This is my custom-built test system for three-phase permanent magnet generator. This video will show you the process of making and testing the system. This is a CAD view of a three-phase permanent magnet generator test system, which was seen in real one in this videos. In this video, we're going to look at the assembly process and the testing process. Please, help me grow by liking and subscribing. I appreciate every one of you. This system consists of a high-efficiency generator and a motor. Let's take a look at the neodymium magnet used in these devices. We will see their operation in the PMSM motor and the PM generator here. In this video, you can see a real 10 kilowatt three-phase permanent magnet generator and a 4 kilowatt three-phase motor. This is the 30 poles stator coil. The magnet turbine has 20 circled neodymium magnets. Before we build the system, we will see magnetic flux flowing through the magnetic flux viewer. This is 1-inch cubic N52 neodymium magnet. The darker the color, the stronger the magnetic force. In this case, if the N pole and S pole of the magnet are placed horizontally, this is how it looks. I will move out the stator coil. The generator is heavy because of the weight of the silicon steel and copper coil in the stator. Now let's look at the magnetic flux inside turbine. In this turbine, the same pattern is seen even though 20 magnets are arranged alternately at the N pole and the S pole, because the strength of the N pole and the S pole is the same. Now let's look at inner surface of the turbine. I am trying to touch the curved rectangular neodymium magnet surface directly. Then let's check the outer surface of the turbine. Right now, no magnetic flux is seen. Now it's time to combine the turbine and the stator coil. Powerful 20 neodymium magnets will attract the stator coils quickly. Turbine axle bearings should be correctly positioned. This PM generator is compact and very efficient but expensive. Let me check the magnetic flux outside the turbine. Here we can find a clear difference. Before assembly, the flux strength outside the turbine was almost zero. However, it's showing differently now. I didn't see any magnetic flux before. The reason for this phenomenon seems to be that the silicon steel material that supports the inner coil has an effect. Now it's time to assemble the power test system with aluminum panels. This is the base panel of the system. All the aluminum parts shown here are custom made by me. This is the system side panel with ventilated screen for system cooling. Now it's time to put it together using screws. The M6 screws were used for supporting the system side panels. I'm tightening the screw with low torque. Once everything is assembled, I will tighten it again. This is the other side panel. Also, the same M6 screws are used. This is the motor supporting panel. Ten 32 screws are used. This aluminum housing is very sturdy and durable. I skipped the recording for the installing of the PM generator because of the difficulty of the camera positioning during the assembling. This permanent magnet generator consists of 20 magnet turbine and 30 pole stator coils. It's time to reattach the side aluminum panel. This panel has sufficient ventilation opening blocks for the system cooling. I skipped a lot because it was boring to keep showing screw tightness. This test system is very robust due to a precisely cut aluminum panels. Cogging torque is mainly caused by the attraction between the permanent magnet mounted on the turbine and the steel teeth in the stator stack. Now it's time to install the PMSM 4 kilowatt motor. This PMSM motor requires a variable frequency inverter for operation, and the motor speed is controlled by frequencies. 4 M13 custom screws were made by a CNC lathe for this motor. This PMSM motor has 8 poles and needs 3-phase AC 230 volt. This permanent magnet. Synchronous motor PMSM is very easy to control the speed. The reason I designed this device in this shape is that this type can most ideally prevent vibration and accurately transmit power. This permanent magnet synchronous motor is designed for 1500 RPM, but I'm going to try to speed it up further than that. This system is pretty heavy. Next, connect the inverter and motor to the power line. The inverter requires 3-phase AC 230 volt or DC 200 volt through DC 380 volt. I choose DC power for the inverter because I can't use 3-phase AC power in my studio. In a three-phase rectifier, among the two terminals below, the left is a positive terminal and the right is a negative terminal. Since this inverter is designed for solar eco-friendly energy, it can also accommodate DC power. Motor power line. For the power of the three-phase motor, the direction of rotation changes when only two of the three lines are changed. This is a ground line. First of all, I will run this motor without connecting the PM generator and the motors. You can see that the input voltage is boosted as it passes through the three-phase rectifier. The DC output of this rectifier is connected to the inverter, and then the DC input voltage rises to a maximum of 324 volt. The left device is a gun-type tachometer. The tachometer gun's power is on now. It's the first operation since I put it together. I will gradually increase the control frequency of the inverter. You can see the RPM on the left tachometer. The cooling fan noise of the inverter is loud. High tone noise is the motor sound. I'll check the revolution every 10 Hertz. Also, I'll just check the motor performance in this video first. The generator will be tested in part 2 video. Let's check the actual RPM and the calculated RPM. As you can see, the measurement of the tachometer is very accurate. This PMSM motor produces high-tone noise which varies depending on the frequency. The tachometer's measurements are pretty accurate so far, right? Let's increase 10 Hertz more. If it increases by 150 RPM every 10 Hertz, it's normal. This measurement is also very accurate. Let's increase 10 Hertz again. This time, the actual RPM is exactly the same as the formula. The RPM has reached 1050 RPM. The measurements and calculation are almost the same. Let's increase 10 Hz more again. The measurements are still very good. This PMS motor was designed for 1500 RPM. However, I will continue to increase the frequency to find the maximum spin velocity. The tachometer numbers are now slightly different from the calculations. I increase frequency 10 Hz again. The RPM of the motor is increasing proportionally as the frequency increases nicely. This inverter can generate up to 400 Hz. However, this PMSM motor is limited to a specific Hertz or less. Let's find out what that limited number is now. Now the RPM is over 2000. Although it shows some mismatch, the tachometer gun is pretty reliable. Let's increase 10 Hz more. Now the RPM is 2250. The next setup frequency is 160 Hz. The measurement is very accurate now. Next target frequency is 170 Hz. The synchronous motor operates smoothly with increasing frequency and still function well. Currently, this motor rotates 1200 RPM more than the designed 1500 RPM. Even if I keep raising the frequency, the RPM doesn't increase anymore, so I think I've reached the maximum RPM of this motor. $27.59 is the maximum RPM number, and the inverter's frequency is 184 Hz. Motor idling test is over now. The motor testing has been completed, and it has been confirmed that the system housing can withstand the vibration of the motor. We can see the real output test of the generator in the part 2. Please, watch the generator output test in the part 2. My contents enrich your knowledge. Thank you for your watching. Please like and subscribe.